Welcome to The Explainer. I'm your host, and today we're unpacking something absolutely crucial, a revolutionary blueprint for our civilization's water survival. I mean, water is literally the foundation of everything we do, right? But the way we manage it right now is rapidly hitting a massive breaking point. Don't worry though, we're not just going to sit here and talk about the doom and gloom today. We're actually diving into a fascinating, highly structured solution to fix it. So let's just jump right in. Here's our quick roadmap for today. We'll start with the global water problem, then break down the THT hypothesis and adaptive water state routing. After that, we'll look at validating the new model, falsification, and wrap up with real-world future implications. All right, Section 1, the global water problem and exactly why the old model is breaking down. So here's the main issue. Our old model for managing water is super simple, but it's, well, deeply flawed. For centuries, our whole strategy was basically just to find one giant, dominant new freshwater source. Think of a massive well, a huge dam, or a giant underground aquifer. We just pump the water out, use it once, and literally dump it. But here's the harsh reality. We're completely running out of those giant, easy-to-reach sources. And as they dry up, the cost to go out, find, and clean new water is just skyrocketing. We simply can't rely on the old, let's just find a bigger well strategy anymore. Now, those rising costs, they're being driven by these massive structural pressures that are all building up at the exact same time. First off, population and industrial demands are just exploding. Meanwhile, our underground aquifers and rivers are totally stressed and depleting fast. On top of that, it takes a ton of energy to treat water, and guess what? Energy costs are going up too. Throw in crazy climate volatility, way more frequent droughts, and old, aging pipes that are leaking millions of gallons every single day, and you've got a total recipe for system failure. When you stack all these pressures together, the traditional water system literally hits a breaking point. Okay, moving to Section 2, the THD hypothesis explained. This is where we see a real paradigm shift in resource management. This brilliant new framework is built on the research of Kevin L. Brown, who's a dedicated researcher, inventor, and author. He developed something called the Triune Harmonic Dynamics framework, or THD for short. Now, he states that civilization needs adaptive routing among all usable water states, prioritized by total system cost, energy load, ecological burden, and resilience value. Okay, I know that might sound a bit complex at first, but it's actually an incredibly elegant and highly practical idea. Let's break down exactly what Kevin L. Brown means by triune harmonic dynamics. Basically, instead of forcing one single water source to do all the heavy lifting, we need to work smarter. When things are under high stress, our water systems have to stop just pulling water in a straight line from point A to point B. Instead, we need to transition to a smart, adaptive network. We intelligently pick the easiest, cheapest, and most available type of water at any given moment. Honestly, it's all about finding the path of least resistance. Which brings us to Section 3, adaptive water state routing. This is literally the blueprint for the future. Think about the internet router sitting in your living room. That router dynamically finds the best, fastest path for data to travel so your favorite show doesn't buffer, right? Well, this blueprint does the exact same thing, but for water. Instead of moving internet data, an AI-driven engine routes water dynamically. It constantly checks all the available sources and instantly sends the water through the best, most efficient pathway. So let's look at what's actually feeding into this system. There are 3 core source layers here. Layer number 1 is the regeneration layer. That's all about reusing what we already have, like wastewater, greywater, and capturing rain and stormwater. Layer number 2 is dense source separation. That's a fancy way of saying desalination, taking the salt out of seawater or brackish-water. And layer number 3, distributed atmospheric. That means literally pulling water straight out of the air by harvesting fog, dew, and even waste heat condensation. But the absolute golden rule here is that we have to use what we already have in layer 1 before we waste energy trying to unlock those harder sources in layers 2 and 3. And tying this whole shebang together is the AI routing engine. This is totally the brain of the operation. The engine takes the local demand for water and matches it to whatever the lowest pressure source is on that specific day. Like if it just poured rain, it routes the stormwater. If it's the middle of a dry coastal summer, it switches over and routes desalinated water. By constantly making these micro adjustments, it drastically cuts down on unnecessary energy use and environmental damage. It's just brilliant. Let's look at Section 4, validating the new model. How do we actually measure this shift? We can totally validate that this shift is happening by looking at real-world indicators. For instance, if you're seeing your water bills go up even after your city just built a bunch of new supplies, that means the old models are failing. If we're seeing more and more drought declarations, well, the system is clearly under high pressure. But when we spot local utilities actually starting to use smart routing, it proves the transition has officially begun. And noticing a big growth in wastewater reuse, that is direct, hard evidence that cities are actively shifting to that first regeneration layer. So you see, this isn't just some abstract theory, it's highly observable right now. Now, there are also these pre-transition warning signals that we can measure. Think of them as the giant red flashing lights before a region faces a total water collapse. We're talking about accelerating groundwater depletion, meaning the wells are running dry way faster than ever before. We see way more frequent infrastructure failures, like constant burst water mains. Cities literally have to start relying on emergency water imports just to keep the taps running. And we see those big desalination plants struggling to expand because the massive energy costs and dealing with all that salty brine waste just become way too much to handle. Section 5, Falsification, Proving It Wrong. This is where we look at the true scientific rigorousness of THD. What's really cool is that Kevin L. Brown built strict scientific boundaries right into this research. In fact, his hypothesis is proven absolutely false if any of the following things happen. First, if severe water stress persists, but cities somehow survive perfectly fine without ever transitioning to adaptive routing. It's also proven false if a single source, say a giant mega desalination plant, consistently beats out the smart tri-source network in both cost and reliability. Or, hey, if pulling water from the air becomes so incredibly magical that it dominates everything entirely on its own. And finally, if we build this adaptive routing but it produces zero measurable improvement, then the theory is wrong. This is what true, rigorous science looks like. But here is a really comforting point about this whole framework. It's structurally stable but totally technologically upgradable. What does that actually mean? Well, it means that if some genius invents a magic new water technology tomorrow, like, super advanced graphene membranes for perfect filtration, it doesn't break this routing model at all. It just makes one of the individual nodes on the network a whole lot better. The overall structure of intelligently routing the water remains completely valid and, best of all, totally future-proof.
Okay, final stretch, Section 6, Real-World Future Implications and Upgrading Human Infrastructure.
This all means we really have to leave our wasteful past behind us. That old paradigm of linear extraction, where we just take water, use it once, and carelessly dump it into the ocean, is totally over. Civic leaders and policymakers have to start prioritizing this new paradigm right now. We need circular, modular, sensor-driven water intelligence. We literally have to be smart about every single drop. And here's where it gets mind-blowing. The implications of this go way, way beyond just water. The rules of adaptive routing show what we call cross-domain transferability. Basically, any system dealing with constrained inputs has to shift to this kind of network eventually. We're going to see this exact same logic apply to our power and energy grids, our global food systems, global shipping supply chains, emergency disaster logistics, and even healthcare and hospital capacity. It's literally the fundamental blueprint for managing scarce resources in the modern world. Ultimately, making this happen requires a massive shift in government policy. Institutions really need to stop just throwing billions of dollars at the largest, most visible water projects just to score easy political points. Instead, they have to start funding projects based on actual pressure reduction per dollar. They need to invest in these incredibly smart routing systems that prevent crises from happening in the first place, rather than just throwing emergency funding at the problem when the taps inevitably run dry. So, I want to leave you with a big question to chew on today. As our primary inputs become more and more deeply constrained, will our civilization actually adapt to route its resources intelligently? Or are we just going to dry up while we wait around for a single new well to be discovered? Look, the science is clear, the blueprint is totally ready, and the choice is ultimately ours. Thank you so much for joining me for this explainer, and as always, keep learning.